Hey, we're back for lesson 15.4. This is the final lesson of new factoring skills that you're going to learn. I don't even know if I would call this a new factoring skill really, because you can use things that I've already shown you in Unit 14 to help you with this lesson. So let's begin. We're going to start with a quick little warm-up. And the warm-up is I want you to multiply these two binomials. So remember the way that that works, you start with the first term and you run it through and distribute. So it'd be x times x is x squared. X times negative 4 is negative 4x. And then you go underneath and you multiply the 4 through the parentheses. So 4 times x is 4x, and 4 times negative 4 is negative 16. We're going to simplify. So we're looking for like terms, which we have 2 here in the middle. And these two like terms, if I add them up, they actually equal 0. So they will cancel each other out. And my answer is just going to be x squared minus 16. Okay? Let's try another one. So I'm going to do 5x times 5x. And I'm going to kind of do the same procedure as last time. So 5x times 5x, that would be 25x squared. 5x times negative 1 is negative 5x. 1 times 5x is positive 5x. And 1 times negative 1 is negative 1. And we're going to do the same thing as last time, and we're going to look for like terms. Those cancel one another out, and you end up with 25x squared minus 1. So let's just talk about patterns for a moment with those two examples. Do you see how both times the like terms in the middle canceled? That wasn't a coincidence. The like terms in the middle canceled because of the way that the two problems were set up. So if you look over here at the two examples, this first one was x plus 4, x minus 4. And down here I have 5x plus 1, 5x minus 1. Do you see how the parentheses are nearly identical in each example, except one has a plus and one has a minus? So when that happens, you're always going to end up with a situation where the two middle terms would cancel. Okay, and it's important to make that connection because that's going to help you do the factoring. And factoring, remember, is where you start with the answer and you try to go backwards to figure out what times what gave you that thing. Okay, so what these are called is these are called difference of squares factoring problems. The word difference is used because there's a minus sign in every single question. And it's called difference of squares because all of the numbers are what we call perfect squares. Okay, so the big thing is for you is you need to figure out what a difference of squares question looks like, and then that will help you to know what to do to proceed from there. So let's answer that question. What does a difference of squares polynomial look like? Number 1, it looks like a binomial, meaning it's going to have two terms. There will always be a subtraction sign in the middle, and every term in the binomial is a perfect square. That's probably a little bit confusing, so I'm going to write you a list of what a perfect square is. Okay, so I'm going to explain it a couple ways. Perfect squares are numbers that have square roots, or you could think of it as like numbers that are created by multiplying something by itself. So like 1 is a perfect square because 1 times 1 is 1. 4 is a perfect square because 2 times 2 is 4. 9 is a perfect square because 3 times 3 is 9. See what's going on? 16 is a perfect square because 4 times 4 gives you 16. 25, because that's 5 times 5. 36, because that's 6 times 6. 49, because that's 7 times 7. And I could keep doing this, really kind of forever. There's 8 times 8. There's not an end to when perfect squares stop, because you could just keep going and multiplying numbers by itself. 10 times 10, 11 times 11. And I think I'll just give you the first, like, I don't know, 13 of them. Okay, so it's nice to have this little list of values in front of you when you're doing these examples, especially if you're someone who doesn't feel real confident in their like mental math skills. At least have this list of perfect squares in your notes. That way you have like a quick go-to, like, oh, is this number a perfect square? Oh yeah, it's right here in this list. Okay, another way that you could tell if a number is a perfect square is use a calculator to take the square root of it. So if it's like a big number, like 225, and you're like, I don't have any flipping clue if that's a perfect square. What you could do is you could say, is this a perfect square? Well, I'm going to take the square root of 225, okay? And what I'm going to do is when I take the square root of 225, I'm going to see if I get a nice even number as my answer. So I'm going to pull up the calculator on my phone and I'm going to take the square root. And when I take the square root, I got 15. And since I got a nice even number, then we would say, yes, 225 is a perfect square. And in fact, it would be 15 times 15 that gives you 225. Okay, so when we do factoring with difference of squares, if we find that we have a problem that fits all three of those scenarios, and those were two terms, binomial, minus sign in the middle, and then all the terms are perfect squares, then it factors out really, really simply. It would just be this perfect square, or sorry, square root of the first term, square root of the last term, and it's going to be set up in a two parentheses situation with 1 plus 1 minus. I'll show you examples, don't worry. I'm going to, before I start the example page, I'm just going to ask you to kind of, as I'm doing this, look for patterns. There is a pattern to it, and once you see that pattern and figure that out, this is going to be so easy, okay? So, I'm going to approach it this way. I'm going to say, is this a difference of squares problem? So I'm going to be looking for those three characteristics. 1, is it a binomial with two terms? Yes, it's got two terms. 2, is there a minus sign in the middle? Yes. 3, are both items perfect squares? So I'm going to say 4, is that on my list of perfect squares? Yep, it is. And in front of A, if you wanted, you could call this a 1. So technically, that is also a perfect square because 1 is a perfect square. It's also a perfect square because A times A equals A squared. Okay, so then if you find that it fits that pattern, you can start to factor. Okay, and watch how easy this is. I'm going to start with what times what equals A squared, so A times A. And we've kind of been doing that in like all the factoring problems prior to this. I know because of the way the patterns work, there's going to be 1 plus and 1 minus. And then I'm just going to say what times what equals 4, but the number I come up with needs to be the same number times itself. So what number times itself equals 4? 2 times 2, and that's it. Okay, let's try another one. So does it fit the conditions? And those are those 3 steps I've outlined on that slide 2 slides ago. So is x squared a perfect square? Yes, because x times x. Is 81 a perfect square? Yes, because it's 9 times 9. And we have a minus sign in the middle, and we have a binomial with 2 terms. So we can factor. Okay, set up your 2 parentheses. Start at the beginning and say what times what equals x squared? X times x. And then what number times itself equals 81? 9 times 9, and you just need a plus and a minus, and you are done. Okay, one more example, and then I'm going to show you a different way to do these for those of you that don't like this technique. All right, let's see if it fits. So 2 terms, check. Minus sign in the middle, check. Is k squared a perfect square? Yes, because k times k. And what about 25? It is on your perfect square list, or you could say, yes, it's a perfect square because 5 times 5 is 25. So this one's going to look like k times k, and then we want a plus and a minus. And then what equals 25? 5 times 5. Okay. Option 2, a different technique if you aren't liking this technique. Okay, if you're not seeing the pattern, watch this, okay? I'm going to do the exact same problem. But what I'm going to do is I'm going to add a little twist. So normally what we were doing, I shouldn't say normally, but what we were doing with factoring before this lesson is we had 3 terms. And we were figuring out what times what equals the third number that adds up to the middle number. You can still do that here. You just don't have a middle term like all the other times. So what that means is that middle term is adding up to 0. So you could still do the little x thing that we went over before and figure out what times what. Let me try that again. And you could figure out what times what equals negative 25. That adds up to 0. Okay, so what times what equals negative 25? That adds up to 0. 5, whoops, 0. 5 and negative 5, right? And that's just going to lead you right back to the other answer that I had before. So I'm using an old skill to do the exact same thing, okay? It's a personal preference thing. Whichever method you feel like makes sense to you, do it that way. I don't care. I have 3 more examples and then I'm going to be done and give you a chance to try your Delta Math. Okay, these are a little bit different because they all have numbers in the front, but you're not going to approach it any differently. So you still need to check and make sure that it's 2 terms, which this one is, minus sign in the middle, which this one is, and that everything's a perfect square, okay? 100 is a perfect square because it's 10 times 10. 9 is a perfect square because it's 3 times 3. So now we can move forward, okay? Here's the difference. I'm not going to have just b times b, right? Because I don't just have b squared here at the beginning this time. This time I have 9b squared. So what would I need to do to get 9b squared? I would need 3b times 3b. You see what I mean? So these 2 numbers will multiply to equal that first thing. And then you can still do your 1 plus and your 1 minus and figure out what times what equals 100. Okay, there's your answer. Let's do 2 more. Okay, number 5. This one also is factorable because it's got 2 terms, has a minus sign. 16 is a perfect square, 4 times 4. 121 is a perfect square because that's 11 times 11. So we just need to kind of fill it in. 16a squared would be 4a times 4a gives you 16a squared. And then 1 plus 1 minus. And you would have 11 times 11 to get 121. Okay. Last one. Oh, I have a little challenge at this last one. So this last one, we have 2 terms. We have a minus sign. 4 is a perfect square because that's 2 times 2. 25 is a perfect square because that's 5 times 5. The twist is that we have letters in the front and in the back, which we haven't had before, but that's okay. We can do it. Okay? So, let's start with the beginning. What times what is 4h squared? 2h and 2h. Okay? What times what would equal 25g squared? So 5 times 5, right, for 25, and g times g, so I need a 5g, 5g. And I need 1 plus 1 minus. By the way, it doesn't matter which goes first, plus or minus. Okay, that's it. Try your Delta Math. See how it goes and let me know. Bye.